So once again, yes, hello, welcome. Welcome to the last week of part 1 of this course. This first part about virtual reality. And this week we're going to tackle maybe arguably the technically most advanced subtopic, namely about the computational complexity of some aspect of simulating a virtual reality, namely via ray tracing, the computational complexity and even the decidability or undecidability of ray tracing. Again, as usual, I take your agreement to be recorded. And that being said, I pass the word and the Zoom display to our speaker. Yes, unmute yourself and spotlight.
Okay. So let me share my screen. Okay, it's good. So yes, hi everyone. My name is Aknur, and today we're gonna talk about the complexity and the compatibility of ray tracing. And the next lecture, hopefully, we're gonna continue this class. So let's start with the history of the ray tracing and application of the ray tracing. So the history of the ray tracing goes back at least to Euclid and his student Archimedes. So the portion of the Euclid's elements were motivated by the Greek interest in the theory of the rectilinear propagation of the light. And in 1730, Newton published his theorized his work Optics, in which he defined the reflective and the refractive laws of the light based on his a theory, and first formally defined and investigated some ray tracing problems. Here the theory of the geometrical optics is a classical field. So in this theory, the propagation of the light is assumed to be rectilinear in a homogeneous medium. And the ray tracing technique uses this assumption. Ray tracing is a valuable tool for designing the and evaluating the optical instruments and for rendering the realistic scenes. So the ray tracing has important applications in the computer graphics actually, and it is used to render the scenes consisting of the objects with the reflective and the refractive surfaces. So the realism of an image is enhanced by the way in which the scene is illuminated by the light source. So a global illumination model called by ray tracing of a visible point in a scene by the following paths of the light rays as they reflected or refracted through this scene. So actually, despite of this great amount of attention paid to the use of the ray tracing, the computability and the complexity of the various ray tracing problems has not been actually well studied. And formalizing these problems by using the assumptions from the theory of geometrical optics, the computability and the complexity can be investigated. So let's talk about the ray tracing problem. What is the ray tracing problem? It's actually the decision problem. So given an optical system, let's say the finite set of the reflective or refractive objects and a light ray's initial positions and the directions, also the some fixed point P. So there will be the question that does the ray eventually reach the P? So optical systems consist of, in this paper, the optical systems consist a finite set of the optical objects that can be maybe reflective or refractive. So the boundaries of these objects may be totally reflective or partially reflective or totally refractive. So in this paper, they restrict the optical systems constructed out of the homogeneous reflective or refractive objects. So the boundaries are described by a linear or quadratic equations. So we can say that the ray tracing problem is irrational if the path of the ray is represented as a union of the light segments bounded by the rational coordinates throughout the system. Otherwise, we say that the problem is irrational. So it seems that the irrational ray tracing problem are not so difficult in terms of the complexity. In this paper, they show that the surprising result that some actual relational problems can be undecidable. So to keep some ray tracing problems rational, they may put some restrictions on the general use of the refractive objects and the quadratic objects. And then so we actually interested in determining if the ray actually will be reached to the given final position. And throughout this paper, they assume that the theory of the geometrical optics and the paths taken by the rays are rectilinear inside a homogeneous medium on the directions of the reflective and the refractive rays are determined by the laws of the refraction and the refraction. So the law of the reflection, the law of the reflection states that the incident angle on the reflected angle are equal, as you can see here. And the law of the refraction states that the angle of the refraction depends on the incident angle and the indices of the refraction of the materials as shown here. And the rays are assumed to have infinitesimal wavelengths, and it can be treated as a lines with zero width. So this implies that there is no diffraction caused by the wave or nature of light, and of course all the surfaces are perfectly smooth, and they not cause any scattering rays on the reflection or refraction. And let's talk about some optical models and systems. So from this paper, the results shows that there is an various optical models can be summarized for these 5 types. So the ray tracing in 3-dimensional optical systems consisting a finite set of the reflective and refractive objects represented by a system of the rational quadratic inequalities is undecidable. Also the same, but the refractive objects are represented by a system of rational linear inequalities can also be the undecidable. And set of the rectangular, reflective, and the refractive objects also the undecidable. And the ray tracing in a 3-dimensional optical system, which has partially reflective surfaces or linear inequalities, where some of the inequalities can be allowed to be irrational. So it's also the undecidable. So ray tracing, the last one is PS-based hard, which is where the set of the reflective and the partially reflective surfaces represented in the system of the rational linear inequalities. So it will be the PS-based hard. Then let's talk about the related works about the ray tracing problem. So some of the actual results presented here were shown by us in earlier papers, but there are several new results represented in this paper, and they actually obtained by considering the refraction and by using the reversible Turing machine. So the first abstract ray tracing problems have also been investigated by Fume. So in his work actually does not describe optical systems, but it considers the symbolic systems. So it can transform the intensity of the rays without any consideration of the geometry of like optical systems. So he showed us that if amplification of light intensity was allowed, it will be the abstract of the like ray tracing problem will be the PS space complete. If there is no amplification is allowed, it will be the NP hard problem. And however, like in his work, he showed that the problem became like in his work, he like transformations on the intensity of rays will require active optical components and with non-linear transfer functions. So actually, these optical devices are not purely optical devices. And also similar like undecidability proof has been like independently obtained by the Moore, who investigated the undecidability in dynamical systems. In his work, he showed us that the motion with a few as 3 degrees of freedom and the smooth dynamics can simulate universal computation. And in contrast, in this paper, the results do not actually depend on any intensity of the rays. So instead, they encode the problems by the positions of the optical rays. So manipulation of the positions is carried out by used by pure geometrical optics. Because of these all considerations, in this paper, the models give results more appropriate to the computational geometry. Then the optical system. Here's the computability and complexity, and we're gonna talk about the optical system and the Turing machines. There is a first optical model that can be assumed that each optical system consists of the finite set of the reflective objects with linear or parabolic surfaces, or refractive objects with a linear or hyperbolic surfaces. So the first subcase, which is the reflective objects with linear and parabolic surfaces, does not require any refractive object at all. But in the second subcase, we may need some reflective objects. And since the reflective surface may be implemented by using the total refraction from the object. And also here, it will be restricted to use quadratic surfaces so that the positions and the tangents of the reflected rays can be traced in the rational coordinates as shown here. And for the Turing machines, in this discussion, it will be assumed that we will assume the reversible Turing machines. So reversible computation consists of the sequence of 1-to-1 and deterministic operations, and it also consists of deterministic to backward. And a Turing machine is said to be reversible if the transition function is 1-to-1. Then we also need some simulate, the simulation will show that the Turing machine can be simulated by any optical system. Here we view that the optical system as a set of the complex optical boxes. We later gonna talk about the simple and the simple and the complex boxes. So each complex boxes corresponds to one state of the Turing machine's finite control, and it implements the transition functions defined for that state. Also, the ray enters the entrance window and exits out of the one of the two exit windows, depending on which state actually Turing machine may enter next. So the system then after this system projects the ray onto the next complex box while preserving the coordinates of the ray relative to the window. And it simulate the transition of the states defining of the Turing machine. And this is the general idea, like how to simulate the Turing machine with this optical idea and optical model. And next, I think we're gonna describe the idea in more detail. And also there will be like represent a storage tape by M by using two binary fractions of U and V. So U initial will be like a symbol at the tape head, and there will be like successive symbols of the U. So as shown here in the first figure, and then we can represent the storage tape by using the two numbers, also the U and V. And since these numbers are between 1 and 0, we can represent it like here in a unit square. Yeah, like lying in a unit square. Also, let's talk about the operations on U and V. As you can see here, like the values on U and V can be like shown like here. After that, like transition, and also after some computation, we can implement the complex boxes that can read the ray entering the window. Also, perform the transformations listed above. Also, then we should actually redirect the ray to a complex optical box corresponding to the next state, and we'll have some succeed in simulating the Turing machine. Next, we're gonna describe the complex box, how to build this complex box to use all of these operation and the computations. But before explaining the complex box, it's better to actually divide all of the complex box contains the basic boxes, and we can discuss the basic box types, several basic box types. So the first one is the readout box, and here we can assume that the U and V are represented as the position on a unit square lying on the XY plane. Or also here the readout box uses two flat mirrors, as you can see here, and these mirrors are reflective, or it can also use the two prisms. Also should be like a two reflective, totally reflective prisms. So they make an angle like here. And the figure of this like shows the several views of like different angles. And the ray enters the box from the unit square on the XY plane, and also it hits on one of the two flat reflective surfaces in the box, and then we call the unit square through which the ray enters the entrance window, and the window size should be between these ones. and so it can actually exit the box from the exit window. After all of this, we can observe that V maintains its value along the Y axis from the entrance window to one of the exit windows. But for the U, it actually loses its value along the X axis. But after the half of the journey, they obtain the along the Z axis. So there will be no information lost here. And there is one type of the basic box. It's a multiple tube box or divide box, very similar. So this box, actually we need this box also to perform the multiplication by two operations, use it in the equations as I have shown before. This can be done by using the pair of cylindrical parabolic mirrors. Also, this is of the reflective surfaces. Or we can use the pionoconvex hyperbolic lenses. But this one should be the refractive surfaces, which placed with the rational endpoints. And similarly, we can use the terms the entrance window, the exit window to denote that the window through which ray enters and the window the which ray exits. Also, there is a basic box, the beam turner. Here. We may need this box in order to change the direction of the ray by half n. So this box actually can be merely a mirror or prism at this angle. And if the using prism, we assume that the index of refraction is greater than the half of the x, then it can cause total internal reflection. And also we can combine these basic optical boxes to construct complex boxes and implementing the transition. So this is the complex box. It's the left move. So here, as you can see in this operation, U and V, we must actually configure boxes to project at this ray at this point. And this figure shows that the physical implementation of this function. So for each state, there is this separate complex box here, and it's the box in the middle is a readout box, and that reads the U initial one, and we call the unit square at the readout box at the entrance window. And also the ray comes out of the plane parallel to the Z Y plane, and the Z coordinates on the plane represents the value of this one here. We got this value here. Also, the ray which exits the multiple two box. After this, there is multiple two box. They goes to the divide two box, and this actually halves the value of the V. And here, the ray which exits the divide two box enters the entrance window of the state Q with shifting by this value. And the path that will be taken if the initial one can be 0. It can be similarly organized here, and the ray can enter the entrance window for the next state of the days. So to get this implementation left moved, this is the physical implementation of these functions. And there is also the right move, which is the similar to the left one, but here we should get these functions. This is the physical implementation of these functions. So we have the readouts box. After this, we need the divide to box. Also, there will be the readout again, and after that, we should multiply the use the multiply to box to get these value. And I think it's this is my last slide. So we're gonna talk about the undecidability. So by simulating each function as a complex box and routing the rays between the boxes, we can use the beam Turner box, and we can simulate any reversible Turing machine, and in particular some deterministic reversible universal Turing machines. So the number of the complex boxes which we require is equal to the number of the finite states of the Turing machine. So each complex box consists of the finite number of the basic box. If the number of the complex box connected to the Turing machine, but in one complex box there is some finite number of the basic boxes that can be represented in rational coordinates. So to show that this model can indeed simulate any universal computation, we can use that, we can employ the Bennett's result to simulate and the deterministic reversible Turing machine. So as you can see here in this figure, there is 8 zones of the exit window in here. If there is more than one exit window, which must be routed to the entrance window, each exit window must be partitioned into several zones. So we have here 8 zones, and these zones must be interleaved and routed to the entrance window of the Q value. And each exit window must also partition it into several zones. So there cannot be any overlapping of the zones from 2 distinct exit windows. Every zone should be have own area, and when simulating the Turing machine, there will be it will be executed one-to-one transitions. And after all of this conclusion, optical system simulations in some reversible universal Turing machine, we can have this theorem. And in this theorem, it says that the ray tracing of the 3-dimensional optical systems consisting of quadratic refractive or refractive objects is undecidable, even if all the objects are represented by the system of the rational quadratic inequalities. So from all of these Turing machines, the simulations, the optical systems, also the basic box that we used to make the complex box, we got this theorem that the objects is the ray tracing the 3-dimensional object system can be undecidable in this part. So yeah, I think this was my last slide. I tried to cover all these parts before the how we're gonna continue more detailed technical parts. So yes.
Thank you. Thank you.
Oops.
So yes, as I said, this is a very technical part. It involves Turing machines, which I myself avoid in my lectures. So yes, maybe is there some way you could kind of close with a short summary of your presentation, of your talk, the things that the audience kind of should remember for the next talk, maybe a few key points or key messages, not too much. You're muted.
So for the next, like how we're gonna do more technical part and explain the other optical systems, optical models. So I think the main key points you should remember for the next class is that there are some basic boxes and the simulations that we use the reversible Turing machines, and that in this part we found out that it's the undecidable, and also so the ray tracing problem what that we're discussing here is a decision problem, and it's in the end what we want have the answer for the question, like does the eventually the ray reaches to some point, and yeah, I think it's it's the key point that you should remember for the next class.
Thank you. Okay, now we proceed to the discussion Q&A session, Q&A part. Regarding the content, please refrain from addressing the quality or providing feedback. That's for later, but now questions, comments regarding the content. Everybody.
I have one question. I didn't really understand that why this ray tracing problem is important for virtual reality. So could you explain specifically for yes?
So as I understood that ray tracing problem is it has applications in the graphic in some like rendering the images, graphic designs. For the future reality, I think you need all this stuff to make this, and so the ray tracing has like a important application in computer graphics, and this is what we're using for the virtual reality. And in this paper, they want to have more attention on the computability and the complexability of the ray tracing problem. So like in the virtual reality, the realism of the image can be enhanced by the way which scene is illuminated by the light source. So that's why we call this is the ray tracing, and it's based on the geometrical optics. So I think it's just connected with the computer graphics, and it's connected to the VR thing.
Thank you.
I have also a question. So irrational number is not concluding that arbitrary irrational number is whether irrational or rational is not decidable, right?
So like so in the ray tracing problem, we can say it's the rational if it has some boundaries, the rational coordinates, and if otherwise it doesn't have but like some actually, because if it has some boundaries, we can actually conclude that it doesn't have any complexity difficulties in terms of the complexity. But in this paper, they find out that that this can be some results that the rational problems can also be undecidable. Irrational bisemidals are also undecidable. So that's why they are talking about undecidability here, because some rational having the rational problem, like a rational path, even if we have the rational path, it can be also the undecidable.
I just curious about, I thought one situation that if we have unisquare with or boundary with totally reflexible and the object coordinate of object is irrational, and if we shot a laser at the origin with slope L, then this problem is related to if we extend this, then this problem is related to subspace of R square with the line first order linear line passes rational coordinates or not. So I was just wondering that irrational number is related to this kind of problem, and thank you for your answering.
Oh, I answered correctly.
Yeah, I guess generally speaking, if the input of a problem involves irrational numbers, then we have to think very carefully about how to encode them and inputting them into a computer. And then it's maybe not really a relevant problem when such coding issues matter. So being able to restrict to rational inputs, then the coding is kind of straightforward, right? So we use rational means the fraction numerator and denominator, both integers, both being encoded in binary, and then there's not much to worry about whether this is a good encoding or bad encoding, because it's just a natural encoding. So being able to avoid irrational inputs makes the problem, how to say, much more natural. Other questions? These were great questions, by the way, and great answers. Yes? So, Zhou Yujin, I think you asked about the relevance to virtual reality, right? And yes, you answered that question very well, Aknur. But of course, it's also true that there are other ways of rendering graphics in virtual reality. Ray tracing is one of them. And what we've learned today, well, half of it we've learned today, is that in general, using ray tracing to create virtual reality for computer graphics can be very expensive in terms of computational cost, and possibly even undecidable, so impossible in the general case. There are other investigations about other approaches like radiosity and so on, but these are not the topic. Maybe one can have an entire advanced lecture on various computational complexity of various rendering methods. But today and on Thursday, we want to discuss and learn about the computability and complexity of ray tracing as one possible way of creating virtual reality vision. Thank you for that great question.